So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Mu-En Liu from National Cheng Kung University, who will give us a talk on large parts are generically entangled across all COTs. So Mu-En is actually like one of my collaborators for this work. Mu-En is a master's student supervised by Professor Yong-Chun Yang at NCKU. Mu-En actually did his thesis defense last week, I think. So he will be doing a PhD with Jean-Daniel Bancal in where is he in France? I forget. Is he in Paris?
Yeah, it's in Paris. It's in University of Paris, actually.
Okay, I see. Yeah. So Mu-En is mainly interested in like problems in entanglement theory, Bayesian non-locality, and its relations to quantum foundations. So Mu-En, the floor is yours.
Okay. Thanks for Jello's introduction. It's really a pleasure and an honor for you to have me here. So today I would like to share with you our recent work. The title is Large Parts Are Generically Entangled Across All Cuts. And okay. So as Jello has mentioned, this is a joint work with him and also the other collaborators. So first, I think Jello, and also Kai-Shan Chen, who is a senior in my lab, and Yongchen Liang is my supervisor. And we also have Zhong Yun in the team, who is now a postdoc in Bristol. And so for the following talk, it will mainly be based on this work, which is now on arXiv. So today, the first thing is that we will focus on the marginal entanglement in generic pure states. So imagine that we are now looking into the parts of the entire pure state and we ask if it's entangled or not. So before doing that, we'll first go by reviewing existing results. And then we'll try to see what we can do with it and say something about multipartite marginal entanglement. And as an implication, what we can do is to say something about generic entanglement transitivity. But before knowing the notion of entanglement transitivity, we first have to know another notion called global unique compatibility, which is a concept related to quantum marginal problems. We will see it later on. And we can even see that for generic pure states, this property is ubiquitous for most pure states. You can observe this kind of property, and we will harp on this concept many times later. And then using all these concepts and the previous results, we can say something about entanglement transitivity in generic pure states. Okay, so let me first introduce you what we mean by saying a pure state is generic. So imagine that now you're sampling states from the entire space of your, and if you do the correct sampling, that means that so every pure state has a chance of being sampled by you. Then we say that the state that you obtained from this proper sampling is called a generic pure state. But one might argue that saying that you're doing the sampling correctly is sort of vague. So you can make it more specific, saying that now I want every pure state. So the chance of sampling every pure state is the same. And so this sampling is further called uniform sampling. And the state that you get by this mean is called a hard-rendered pure state. Okay. So we will harp on this concept later. So why do people want to study these kind of states? So as we know in quantum information, many topics are very hard, very difficult. But in contrast, if you only want to know the average properties of how most the average properties of quantum states, then because it's analytically attainable, so comparing to getting general statements, it's more tractable in this sense. And then people realize that actually looking to the average properties is useful in disproving conjectures or finding desired examples, because now you sort of can describe the average properties of quantum states in an analytical way, and that helps you to even show that some conjectures are not true. So for example, if you look into how the average properties of quantum states, you can find some very peculiar entangled states, those having properties that sort of a surprise to the people in the field. And so arguably, the purpose of studying generic pure states is because that people want to disprove the additivity conjecture, and which is a success. And for more recent progress, people have used the knowledge of generic pure states or random matrix theories to say something about the PPT square conjecture, so which is quite exciting. But people can also argue that knowing the average properties actually is not enough. But what people also know is that knowing the average properties is actually quite useful, because most pure states behave similarly, and that means that if you look into the average properties, you sort of know how most states behave, because the deviation from the average property is not so much. And this is called the concentration phenomenon. So, one of the most famous examples is that if you look into high-dimensional pure states, then most of them will be highly entangled. So the specific details, I will show you the specific details later. So I think it's a great timing to emphasize this point, because people have observed that actually when we go into specific and suitable dimensional regimes, then most entities tends to have the same behavior. So maybe I can quote Levy's words here. Ago, that an increase in the number of variables might cause simplifications, which is quite surprising. So in physics, it is meaningful to know how quantum states behave in general. So studying how generic pure states behave is actually interesting in its own right from the physical perspective. So as you know, in thermodynamics and statistical mechanics, people are looking into the average properties of how physical states behave. And even now, in the field of quantum information, we can use the knowledge of generic pure states to say something about the premises in thermodynamics. So we are also having the same sort of philosophy, namely, we want to know how most quantum states behave from the perspective of physics, and more specifically, we want to discuss the entanglement of the parts of generic pure states, and also the concept called uniqueness, which we will see later. So let us dive into the topic by first seeing what are the existing results. So later on, you will continuously see this scheme. So for each circle, it represents a party. And so jointly, these two parties form, you can imagine that they form a global pure state, a global bipartite pure state. And we will call the part a marginal of it, which can be obtained by just partial tracing the entire global state. So what people can know is that when you look into most bipartite pure states, it seems to be very likely to be entangled. So if you walk on the street and you sample a state, and so very likely you would encounter an entangled bipartite pure state. But that is not just that, because you even know that it's highly entangled. So what do I mean by that? So what people can do is to establish this kind of relation. And by saying that it's highly entangled, it just means that when you look into the von Neumann entropy of its marginals, you can show that it is not so far from the maximum it can obtain. So by saying very likely, it just means that the deviation from the von Neumann entropy of your marginal to the maximum you can get is upper bounded by exponentially decaying term, which means that it's very unlikely for it to have a large deviation. And here C is just a constant. So far, so people know that the entanglement of bipartite pure states. So basically, we know that when you look across this bipartition, you know that these two parties are entangled. But in the lab, we sometimes can only have access to parts of the pure state. Also, it is not guaranteed that your target system is not coupled to the environment. If that were the case, then you have to admit that your system is also a part of it, some larger global state. So this is effectively a tripartite state if you do some grouping. For example, if you group one of the parties into two parts, so now the pure state as a whole is composed of three parts, actually. And now you can ask whether this part is entangled or not. Good. Okay, so what do people know about this question? Is that, okay, so now we are focusing on A and C, and let us further assume that A and C have the same local dimensions. So what people know is that when the AC marginal that you're looking at is sufficiently small, then it is very likely to be separable. So it just means that when the size of B, the other part, so when the size of B is larger than a certain threshold, then the probability for AC to be entangled is again upper bounded by some exponentially decaying term, which means that AC is very unlikely to be entangled. So what is S naught here? So S naught is a threshold in between these two values, and these two values are can be characterized by the dimension of A and C. And so if you want to say that A and C are sufficiently small, then you have to first assume that B has to surpass a certain threshold. And if B is larger, then you can even say that the probability for it to be entangled is very unlikely. So that's what I mean by saying AC marginal is sufficiently small. So you can also make similar statements for the opposite. So again, it says that when B is smaller than this threshold, meaning that AC is sufficiently large, then the probability for AC to be separable is again upper bounded by some exponentially decaying term. Yeah, and you can also see that here large A and C are required. Good. So okay. So now we know that when we have small ACs, then they will very likely to be separable. But when we are looking into the part which is relatively large, then you can say that it is very likely to be entangled. And people even know about what is the threshold in between these two phases. So for when B is larger than this threshold, it will be very likely to be separable, and otherwise it holds. So this is a or non behavior. By saying it is an or non behavior, it just means that the transition from one phase to the other is very sharp. So when you have this phase transition, when you have this transition of phases of marginal entanglement, the transition is not smooth, it's rather sharp. So it just means that in any dimensional regimes, okay, in suitable dimensional regimes, what you will see is that the vast majority will either be all entangled or all separable. Good. So now people know that when dB is smaller than this value.
Can I ask a question? Sorry, can you
sure.
remind me what was S0? I'm sure you said it, but I was probably reading something.
Yeah. No, I only quickly go through it. So okay, so yes, thanks for the question. So S0 is a threshold, and what is it all about? It says that when B is larger than this threshold, then you can say something about the entanglement of AC. And S0 is actually in between this range. So maybe this is much more useful. So here, as you can imagine that this dashed line is just S0. Yeah.
Okay, but I mean, what do we is there any conceptual input as to like how would I think, like, is there a way to know what this threshold is, or is it just found numerically, or how do you you know, if you're looking at a system, can you have some intuition about where the threshold is, or?
All right. Yeah, you can actually. Yeah, that's a good question. So you can actually, by looking at what the size of your A and C's are, and then you can know the range of your threshold. So yeah, so you can either numerically calculate this threshold, or you can even already say something about it by just looking at the size.
How big are little c and big C?
All right, that's a good question. Roughly, like, okay, so it's kind of okay. I sort of forget about it, but if you look into the papers, you can, yeah, say something about it. Yeah, okay. Yeah. So I think in the field, people are trying to make this log term to be something polynomial, and yeah, so you can make the transition to be even sharper. Yeah. Okay. Thanks for the question. So now we have this intuition.
Sorry, can I just follow up? I mean, I guess I should know, but I will ask you. Like, I guess like in some sense, like can we have some intuition why would we expect it to be something like d cubed?
All right.
I mean, roughly, I would think that
have,
there's some kind of like parameter counting that you can do that will tell you why this is the case, but it's not. I guess it's not so obvious.
Yeah, it's not so obvious. So what people have to do is that there are some tools in something like asymptotic geometry, and can sort of say that for states having certain properties, what is the volume of for these states, and you can sort of say the ratio for this volume and the volume for states that do not have this property, and you can use like geometric tools to make these statements, but it's not very obvious if you just think in the way of parameter counting. Yeah, that's what I can say about it. Yeah. Okay. So thanks for the questions. So now, what I want to stress on is that we now have this intuition that looking at the size is sufficient to say about how likely your marginal is entangled or separable. And now, so let me just do a recap. So when the size of B is smaller than like D cubed, it is very likely for AC to be entangled. But if it's larger than the size, it's very unlikely for AC to be entangled. But now you may want to ask, can we find some condition such that the probability for AC to be for AC to be separable is actually 0? And yes, we can do that. So what people know is that if B is smaller than the size of A and C, zero from sight, because now it's just the size of A and C, then the probability for rho AC to be separable is actually 0. So, for example, if now A and C are of the same size, you can say that when B is smaller than D minus 1 square, then it is almost surely for AC to be entangled. So by saying that it is almost surely, it just means that the probability for an event to happen is like probability 1. Good. So not only we can say that like large things are very likely to be entangled, but they're even generically entangled. So by saying generically, it means that like all of them have certain kind of properties when you sample the generic, when you do this kind of random sampling. And another thing that one can be noted is that the relation only depends on the local dimensions. So looking at the local dimensions, which is relatively easy, is enough to say about the entanglement properties of the marginals. So this looks like magic. So I would like to walk you through like the key steps in the proof of how people can make these statements. So first, we can observe that when we look at the bipartite marginals of tripartite Hard pure states, then we can see that the support of these bipartite marginals is actually a span of many bipartite Hard pure states. And this observation actually tells us that the span is also a random subspace. And so why is it so special about this random subspace? So for now, you can just ignore this term and just imagine that, okay, now the span is just a set of bipartite Hard pure states. So what is special when we see that the span is a set of Hard pure state is that this subspace would be completely entangled. So what do I mean by completely entangled? It means that this subspace is void of product states. So inside the subspace, you will not find any product states within it. And that just helps us to do the job, because if we know that a state is supported on the completely entangled subspace, then we can know that it is entangled. And this follows from the contrapositive that by observing that separable states, the support of separable states must include some product states. So when you see that your support, there's no product states within it, you can conclude that the state you have must be entangled. So that's the reason for why people can make these statements. And you can observe that what is really hard is the first part, by showing that the span is, the second part, so by showing that the subspace is completely entangled.
Is this, I guess, can this statement be made robust at all? I mean, it seems like it's, you know, it could be extremely close to a product state or extremely close to separable, but
Yeah.
in this, can this be made robust in any way?
I think that's kind of interesting, because I haven't seen literatures doing that, but it'll be interesting to see that you can make statements saying that subspaces are like epsilon close to. Okay. Okay, so now we have some new criteria of entanglement, and it's to compare it with existing ones. So the one we're using here is a distillability criteria. So for a state to be distillable, it also implies that the state has to be entangled. And the reason why we are picking this criteria is actually because it also only depends on the local dimensions. So when the local dimension satisfies this complicated like relation, then you can see that, then you can show that rho AC would almost surely be distillable, meaning that it will almost surely be entangled as well after some local filtration. And the sufficient condition looks quite complicated only because we're looking into horror pure states, if you look at general pure states and you use this criteria from this paper, then it suffices to look at the rank of the marginals. And by just looking at the rank of the marginals, you can make statements of distributability, which is quite good. Okay. So if you sit down and do some math, you can show that having the second condition will imply the first one, but vice versa does not hold. So when local dimensions are the same, you can already see that the first one does not imply the second, which means that the first actually identifies more entangled marginals of generic tripartite pure states. So we can, from here, we can see that it's not so trivial to consider this new criteria. Great, so now we have gone through what people know about the bipartite marginals. So now we want to play around with these existing results and see what we can say about multipartite ones. So initially, we're looking at bipartite marginals, but if you look closer, then perhaps you can see that for each party, it is actually composed of many more constituents or particles. Good. So now assume that A and C are composed of many different qubits. So here, for each ray circle, it represents a qubit. You can imagine that the entire one is a Hall-random pure state composed of n qubits. Good. So then we look at, again, looking at AC marginals, but now effectively it is a k-qubit marginal. So using the previous results, you can also say whether it is entangled across this bipartition. Nothing new, but if you can also ask under which condition would it be entangled across any cuts. So now this is only one of the possible cuts you can make, but you can also make the cut here and there, and you can ask, so what are the conditions for this marginal to be entangled across any cuts? So by saying across all cuts, I just mean that n can be any value in between the range. So n is just the size of C. So it can either be composed of just one qubit, even just k minus one qubits. So if you sit down and do the math, you can find sufficient conditions for this. What's surprising is that you can see that the qubit number for this marginal, it just has to exceed like half of the size of the global state. This is for general cases, but when your pure state is composed of odd number of qubits, then you have to use a slightly stricter criteria. And you can imagine that this can be done by using the result that you have just seen previously. You can just recursively apply the criteria to each cuts, and you can obtain this result. Good. So initially, we know that it's generically entangled for large parts. But now we can even show that it is this even holds for any cuts. And so if you can even compare the result with other existing ones. So for existing ones, it's it's in the line of saying whether an event is very likely or very unlikely. So what is quite sort of cool is that you can see that the bound is not so far from existing ones, which is also half of the size of the global state. And so perhaps the physical meaning for this finding is to say that if you now have a Hall-random pure state, it must be very expensive. If you now have a Hall-random pure state, and if you just lost something, you can still have it even if you lost it, and the marginal will be entangled even you lost nearly half of your qubits. Okay. So to illustrate more of this entanglement property of marginals of hard-random pure states, let us look into a entanglement sharing game. So imagine now I'm the referee and I'm distributing a pure state composed of n qubits to a group of members, a group of players. And the rule is that it is desirable for a group, so they have to, so each members have to find their own alliances, and it is desirable for this group to have an entangled state within the group. Okay. So you can show, because of the previous results, saying that the KQ trit, so now for simplicity, you can consider Q trits. You can imagine that for now, you have KQ trits, and the KQ trit marginal will be almost surely entangled across all cuts when K is exceeding half of the size of your global state. And what will this property do is that now you can enforce at least this amount of members to collaborate together. So because so in some quantum information protocols, sometimes a certain size of the collaborating group, we would like this size of group to exceed certain value. And this property just enforce that, okay, at least this number of members should collaborate together. And what is more interesting is that they do not need to form alliances before the state has been distributed. So imagine that now I distribute the state, and now in everyone's hands, they have one qubit for each person. And so no matter who they're going to find to be their friend, to work together, as long as there is this amount of members, they can know that the state that they have within the group must be entangled as cross cuts. So so you don't have to decide who to collaborate with before the state has been distributed. Of course, one might see that this is rather qualitative. We do not quantify how much entanglement there is, and we are not using specific entanglement measures. But still, this is just a concept of to illustrate this nice property of marginals of hard-random pure states. We can see that if you have a task like this, you can see that hard-random pure states may be a potential resource. Good. So another implication another implication for this generic marginal entanglement is a phenomenon called entanglement transitivity. But before that, let us look into some concepts related to quantum marginal problems. So when we say that, so now if you have two states, let's say it's rho AB and rho BC, and if we now say that they're compatible, it just means that you can find some other tripartite state that simultaneously have the two marginals. So more specifically, it means that there exists a tripartite density matrices such that by doing partial trades, you can retrieve back exactly the same two marginals. So similarly, you can, so when you say that rho is compatible with the given two, it also means the same. It just means that they can come from some common global state as well. Great. So now let us dive into the concept of entanglement transitivity, which is done by Jello and other collaborators. So now assume that you have A, B, and BC entangled marginals. So now these two marginals are entangled. And you further know that if you look into any AC marginal compatible with the two, it turns out that this is always entangled. So for any compatible ACs you can have, if you find it's always entangled, then you say that when we say that A, B, and B, C, they exhibit entanglement transitivity. So meaning that entanglement as a property can be transitive, because if you know that these two parts are entangled, it just implies the other part should also always be entangled as well. So let's look into an example. If you look into the W state, if a composed of 3 qubits, its marginals look like this, which is known to be entangled. Good. And what is quite surprising is that the only AC state that is compatible with AB and BC would be this one, which is the same as rho AB and rho BC. So it just means that there is no chance for you to find another state different from this, which can also be compatible with the two, which is quite surprising because a priori you can imagine that their compatible states can be very different. It doesn't from the original pure state. And because AC is the same as AB and BC, you also know that it will be entangled as well. So for this case, you see that AB and BC, they indeed exhibit entanglement transitivity. And let's talk about what uniqueness is. So from the example we have just seen, we see that this state will be the only state compatible with rho AB and rho BC. So this means that if you just look at the parts of the density matrix, you can already know what the global state is. So in some sense, the AB and BC marginals, they uniquely determine what the global state should look like. And if we go back to Horrendon pure states or generic pure states, what is surprising is that most of them have this kind of property. So just like entanglement criteria for marginals of Horrendon pure states, the criteria for this uniqueness also only depends on the local dimensions. So here, let me remind you that, this here, the B is the overlap of the given marginals. So it says that whenever you have these two dimensional constraints, then the generic pure state or the Horrendon pure state, they can almost surely be uniquely determined by AB and BC. So it just means that for most states you get from using or like proper samplings, as long as you know just part, you can also know what the global state is, because you can sort of reconstruct ones from the margins. You can also do some numerical calculations, and we observe that the uniqueness property holds actually in arbitrary local dimensions. Well, we only tried small ones, but small local dimensions, but it seems that it is still ubiquitous. It means that other than, right, hi.
Sorry to interrupt. I just wanted to know, how hard is it to reconstruct the global state in this setting where it's unique?
Okay. Okay, I think maybe your question is, we know that if you know the marginals, in some sense, there's only one global state that is compatible with them, but is there like a very specific way to reconstruct the global state from
you're
just the
given
marginals?
you're given the
Yeah.
marginals and you're promised that it's unique.
Right.
Can you
Yeah.
construct efficiently in the
Yeah.
dimension or something?
Right. So the proof here is not giving us explicit ways to reconstruct the state, but yeah, that's a good question. So I imagine that you can first purify the state, and you demand that the purification also contains the marginals you have in mind. But I guess, yeah, that's kind of yeah, I don't have a very smart way to reconstruct the global state from just the marginals. Yeah, because here the proof relies on parameter counting, so they are not constructing some kind of channels to say that you can reconstruct construct the global state from the marginals. Yeah, which would be interesting if we can find one. And because we already know that uniqueness holds. Yes, Jello.
No. I mean, I just wanted to clarify with when you say like how hard it is. Do you mean like if I give you copies of the marginals and you need to run a circuit to produce the global state, or do you just mean like in a computational sense?
I mean, like, yeah, if someone gives you the matrix of marginals, like as classical data, can you just like efficiently in the size of the input compute the?
Also, like in a computational sense.
Yeah, in a computational.
Because I mean, like you can easily run a feasibility SDP to find the global state.
Okay.
Yeah.
And that SDP is like in the size of the dimension of the input, or?
It should be, yeah.
Okay.
Yeah, but if you start, so here we're trying to utilize the property that now the global states are pure. But if you start from some mixed global state, then there, like to my knowledge, there's no SDPs to do that. Yeah. Okay.
No, I mean, like I think in Hackup's problem, at least you're promised that it comes from pure state or something like that.
You promised that it comes from some pure state.
Yeah. Then in that case, then it can be done. Yeah.
I see. Okay. Thanks for the questions. Yeah. So now previously we have results of uniqueness in tripartite states, and you can also say something about multipartite uniqueness. So again, people can show that if you choose this the size of marginals of the size or marginal of the size, and the numbers of marginals are also specified here, then you know that they will be unique. And you can also ask whether you can minimize, you can even make the size of the marginals to be smaller, and people have shown that this cannot be done. So for illustration, let us see a 7-qubit pure state. So if you have this marginal, this one, and also this one, the free marginals can uniquely determine the global pure state. And there are other ways of grouping. For example, if you have this marginal and this marginal, it is also enough for you to uniquely determine the global one. So from here, you can see that both of the size of the marginals and the overlap matters. Good. So we have seen from the W state that uniqueness plays an important role for us to see that it exhibits entanglement transitivity. And once we know that generic pure states have this uniqueness property, we can go on to say that they also have entanglement transitivity. So we have seen sufficient conditions for generic pure states to be uniquely determined. We also have sufficient criteria to say that their marginals should be entangled or not. Then we can show that entanglement transitivity is generic, meaning that the marginals of hard-random pure states almost surely exhibits entanglement transitivity, and we can obtain a bunch of sufficient conditions by simply combining these two. And for simplicity, you can say that at least when the local dimensions are the same, you can observe this one, which provide the proof for our previous numerical observations. An example of this is that for example, we have this sufficient condition as well. And based on the sufficient condition, you can try to make a smart choice. You assign B to be free, which is just a Q-trait, and you assign A and C to be the same size, which is relatively large. And by this value assignment, you can argue that B comparing to A and C is very small, so you can say that it can be treated as a microscopic system, and A and C are macroscopic. So because we know that for generic pure states in this region, they will exhibit entanglement transitivity. So you know that here, when the small b for microscopic subsystem to be entangled with larger ones, this immediately implies that A and C, which are two macroscopic systems, they will also be entangled. So in some sense, you see that the result implies that the entanglement between microscopic and macroscopic particles, they even enforces the other two macroscopic particles to be entangled as well, which is quite interesting. You can also look into other numerical results. So for the checks and arrows, it means that whether they are the property holds according to norm results. So for A, B, and B, C, and AC, it just means that we're looking into the marginal entanglement. And for this one is the uniqueness properties. So if it's, for example, for the first dimensional regime, we know that the BC marginal is not entangled according to norm results. And for the left-hand side part, it shows the frequency for the state to have entanglement transitivity. So here we're using the PBT criteria. M means that the state will be negative under partial transposition, and P is just positive under partial transposition. So what we can conclude is that first, in numerical observations, it seems that in all these regimes, uniqueness always holds. And if the Horrendon pure state have at most one qubit, so it only has a part that is relatively small, then they can still exhibit MPPT, entanglement transitivity, meaning that when A, B, and B, C are MPPT entangled, it also implies that AC will have MPPT entanglement. But for those involving more than one qubit, our previously established sufficient condition seems to be having very good predictive power, meaning that whenever you have more than one qubit, they will fail to have this transitivity. Good. So in summary, we have seen that first, large parts are generically entangled, and small ones are very likely to be separable, and this is an intuition provided by existing results. What we extend is that we can show that multipartite entanglement marginals will be almost surely entangled across all. For this to hold, you just simply have to demand that their size is slightly larger than half of the global system. Okay, so to put in a slogan, you can say that large parts are generically entangled across all cuts. And as a byproduct, you can show that entanglement transitivity is generic in any tripartite closed systems. And in this talk, we have discussed about the genericity of entangled marginals, uniqueness, and transitivity, and they can hold beyond the analytically established dimensional regimes. And thank you for having me here, and I thank you for your attention.
All right. Okay. Thank you very much for a very interesting, formative talk. Okay, I guess like some people, I mean, like Jakob and I were already sort of asking questions, but okay, we have a few minutes for questions from other people. So if you have questions, feel free to just unmute and ask them now. Okay, is there anyone? Not seeing anyone. Maybe I'll ask a quick question first. So when you talked about like this example where like you can afford to lose almost half of your particles and still have entanglement, right? What I'm curious about is, okay, it's entangled, but how much entangled is it? Is it like the case that the more things you lose, the less
Right.
entangled it gets? Or
Uh,
relative to the number of particles you have, it remains highly entangled?
I see. So what you're saying is that when we sort of quantify the entanglement of these marginals, would this quantification decay as a number of constituents also decreases?
Yeah, I'm just curious, like if this is known.
Yeah, I'm recalling other results. So people know about MPPT entanglement in these marginals. You can also establish a threshold and say whether these marginals are MPPT entangled. But in that case, the negativity is not quantified. And I think if you look into like entanglement of formation, you can, right, that's kind of hard to say. Yeah, to my knowledge, only results of whether or not they have certain values of, for example, like entanglement formation of whatever entanglement measures, they can only establish whether the marginals have this kind of value, but they cannot characterize whether there's decay or increase with respect to this entanglement measure. So I think, no, we do not have this kind of knowledge. Yeah, I do not know.
Okay, it's fine. Yeah.
So this is not a very well-formed question, but I think I won't be able to formulate this question well in any time soon. So I'm just going to ask it. If you relax your, like, I'm interested in understanding like to what extent high randomness is needed. Like if you went to like T designs or something like this, is it really sensitive to the T, like, or is it like, you know, how would you write this in terms of, the moments or something? Like, do you care about having a high degree T or something, or is like 3 design is all you need or something? Or
Right. That's a good question. Although I cannot give you a direct answer, but I can sort of provide you more information. So here, as you can see, many results seems to hold for Hall random pure states. But actually, in the original proofs, the uniform distribution, this property is not explicitly used, meaning that as even though you have a distribution that is not uniform, the properties for this generic entanglement or this uniqueness will still hold. And what does this distribution should look like? It should be so for this distribution, as long as the measure zero set of this distribution is the same for like Hall random distributions or the best distributions, then it should be fine. So technically, like measures. And for T designs, I'm not so sure whether their distribution will have this property, meaning that if you can characterize the measure zero set of T design states and whether it will be equivalent to those for.
well, I mean, they'll be discrete, right? So I don't think there'll be measure zero. Like there will be
Okay.
non-zero probability of making a product state or something.
I see.
It'll vanish, like as T grows, it'll vanish quickly for large N, but I don't think, yeah.
So what you can say is that the measure zero set will not be the same as the Hall random ones.
I think so. I mean, like take like
Okay.
Clifford's, for example. Like a
Right,
Clifford
right.
circuit has a non-zero probability. Like a stabilizer state has a non-zero probability of being a product state. I guess
Right.
that, I mean, it goes to zero as n goes to infinity, but like for any finite number of qubits, it's non-zero.
I see. I see. Right. Yeah, so maybe you can say that. So maybe even one can establish that when t goes to infinity, you can more likely to have these results. Yeah. Okay.
Okay, cool.
Okay, I guess I just wanted to add that, I mean, because one of the last things that I looked at before we were writing this up was I was just curious, like, because I realized that, oh, if you talk about how random, it's not so interesting from a physical point of view, because I guess like states that you get from Hamiltonians are not going to be anything like how random, for example. So one thing that I tried is like, what if I have like this pure states coming from random shallow circuits? So in particular, what I tried is something like with just a few qubits, and then you apply sort of like 2-qubit neighboring gates in sort of like a brickwork kind of structure. And it seems to have like this kind of like uniqueness and entanglement transitivity properties still. So at least like for the small things that I looked at. So yeah, I mean, like in some sense, your question is actually quite interesting because it's not so clear, like to what extent like we can observe something similar. Yeah. And my feeling is that yeah, if you have something that is uh, like even like a coming from a pseudo-random unitary, pure state produced by pseudo-random unitary, my belief is that these things hold. But it's a question, of course, like, can you prove it? Probably not so easy.